Hi, Ryan.
Good morning.
So excited to have you.
Thank you. Okay, let's see if that, sharing my screen. So I was wondering if it's an admin option from your side to make the presentation come up.
There we go.
Go. Awesome. Great. Thank you, Jenna.
Thank you.
Okay, so I don't know if anybody's seen some presentations I've done before, but the topic is test data management and service virtualization. And our earlier versions were around why testers can't test. Well, this is now just more of like slowly dropping off some of the other pieces that were very thorough and now building more into kind of where we are today. And so this is why I kind of rebranded it and added to it and call it our journey. Let's see here, make sure the arrows work. So I'm going to kind of high gloss over our journey real quick. So I started at Alaska Airlines in 2010 as a mobile test lead for our iOS, Android, and mobile websites. So those also depended on our web services. And in order to help test these applications, we used Fiddler. This was great because this allowed us to essentially fiddle with the API responses to force conditions that we couldn't do in the application that were areas we didn't have control over. Well, this is really cool and allowed us to test a lot of cool things we weren't able to. But also, Fiddler has another really neat advanced option called autoresponders. And what that allowed us to do is literally fabricate or record a request response pair and set up a correlator. Mind you, this is free. It only does it for HTTP. But this was essentially, I call it our first step into virtualization. Flash forward a couple more years, we had another SDET on our team who was like, well, this Fiddler thing isn't really working for me. I need to do multiple responses that change over time. And he used Wiremock. And so it worked in a different perspective. It used more of a cursor approach. So each request that would come in sequence would get a different response. Back then, we didn't have all the capabilities that are available now. What we ran into here was when you try to scale up and do parallel tests, they wouldn't get the right response. And so it was really hard we weren't getting consistent results. Today, those problems are now solved. There's, I think, called mock server that can solve that for you if you're going to got automation and virtualization kind of solution. But in 2014 is really when, if you talk about the hockey stick approach, like what really changed for us and to get new capabilities. And for us, this was adopting Parasoft Virtualize for a large project that I'm going to go into detail here during the presentation. What this kind of tooling does, not only does it do HTTP, but allowed us to do other protocols, SOAP, REST, MQ, database. And it is like a full, I'll call it a big hammer solution, which can solve lots of different problems very, very fast. Well, then our next step in 2017, after working kind of through these little baby steps of evolving through our solutions, we started kind of building our own solutions using lightweight web services and what we like to call engineered test data. Engineered test data is just a quick glimpse. This is like my own personal branding. It's not recorded data. It's actually purely engineered. It is designed from ground up and fully synthetic. And so this is the tail end of this presentation is actually a lot of our efforts in this space. So let's look at our earlier showcase of some of our solutions so you can kind of see the baby steps of how we evolved. So Proxy Recorder. This is essentially that Parasoft virtualized toolset out of the box, allows you to set up a proxy in between your client and your services. What's really cool about it, it gives you a monitor so you can see the requests and responses in real time. So that gives you visibility. And that actually saved us quite a bit of time because the old way, we would actually have to go into another logging tool to see what happened. But now you could see it in real time. Another cool ability this gave us is scaling, is bridging and cloning. We were running up to 7 environments. And so we would actually have one feed recorded from one environment, and we're able to now record that and broadcast it to all these other environments. we kind of built on this solution. The tooling they used early on was essentially a OrientDB NoSQL database. And our guys, we were hyper efficient and super fluent in T-SQL. So we actually adapted their tool to use a SQL backend instead. And mind you, this is not recommended or advised. It just happened to be, we're like, we don't have time to figure out something new. Let's just use what we know. And so we were super quick in putting that together. And that gave us these really cool capabilities that actually helped us in these next steps. Now that it's being recorded to a SQL database, we could use XPath and XQuery to analyze the data and then start to do these really cool, I'll call it this baby step to get to engineered data by now transforming it. Okay, so we now have this like recording and playing back. Well, this next step is building on those transforms I was talking about. We were able to record scenarios, but the training team came to us and said, we need all these scenarios. We need to train a lot of people at once. And we want these bits and pieces out of the environment. So I'm going to, just so you know, this is a future slide. I'm going to show you actually the UI and what this solution really looked like. So we ended up cloning, creating synthetic aircraft so we could handle parallelism, but then also using our, I'll call it the engineered data approach for creating condensed flight durations. And this gave us very extensive training opportunities, which I'm going to go into more here in a few minutes. Okay, we're building up on this capability. So our automation team is like, hey, I'm seeing you're doing this recording, you're giving us consistent data in this one environment. I now see you scaling that data to solve these other problems in the other environment. Can you give us the capability where you can just give me data on demand? If I give you a request saying I want this flight and I want it in this D- state, D- is departure minus minutes from when it's going to depart, and I want it in this specific environment. So since we had that recording, we actually took and built our own fake web service, built our own API specification, and have it reach into our database of recorded data, apply those transforms, and route that data to whatever environment they specify. This gave us massive amounts of automation capabilities for getting consistent data. And so our BUAT team could be building scenarios in one environment, and they're like, hey, we want you to run this regression on it. He could just retarget his framework saying to go run these new scenarios against that environment, but then still be running them in our other environment. So this is just, I'd say bar none, one of the coolest things we've done. And this in detail could be its own presentation. Next is this passenger services. This is kind of a sidecar only because it's so big. Literally, this could also be its own presentation. We're running an airline. We have customers going through the life cycle of booking and checking in and boarding our aircraft. That is all stored in a real Sabre mainframe. Sabre is a GDS, which is a global distribution system. So all the airlines can take and share ticketing capabilities so you can book connecting flights. Well, there's a per hit cost on this. So what we ended up doing is virtualizing the Sabre Sabre service wrapper around that. And by doing that, we started off doing recording. So it's just now just kind of a lot of recording, but now we are doing the transforming and making what we want, not versus what we got. And so that's kind of more of that transition to engineered data. Well, once we've now parsed this all to SQL, our behind-the-scenes SQL database, we now have massive capabilities. Cool things here for us as an airline are simulating all passenger codes. There are like special business rules for like for disabled seats, or if there's a wheelchair or oxygen or pets in cabin or pets in cargo hold or dangerous goods, where to store them on the aircraft. This allows us to test all of those cool scenarios that we need for this flight operations weight and balance system. Also, these other neat capabilities we have, since it is essentially a table, we could do adjacency and Cartesian and referential seat mapping to load up new rules. mind you, this isn't rules in the system. This is rules in the test data. So a good scenario here is an example is like Seattle to, it's not Burbank, but John Wayne Airport to go to Disneyland. Say we have an aircraft with 150 seats. Okay, so we have 150 seats, but that's going to be a lot of families with a lot of young children. That creates a lot of unique scenarios for weight and balance. And those scenarios are essentially we go through adult, children, and lap infants. Say if we had, easily could have, 5, 10 families going down to go to Disneyland, but let's say several of those families have lap infants. You can easily have 10 lap infants on the aircraft, which now you would have 160 people in 150 seats. So this creates a lot of nuance for testing our weight and balance system. And so this was, again, could be its own presentation for all the detailed work we have here. One of the pieces I haven't really talked about is it also uses time event modeling. So it actually, as time goes on, the responses keep adjusting based on essentially these programmed curves we put in for what's the percentage of people loaded through the different states. So it actually looks like a real service when you interact with it, but it always ends up on the final answer. It's really given us so many great capabilities for testing our systems. Our system, okay, this is it. This is the system I'm talking about. It's in the middle, and this is the actual architecture diagram for it. It's been, fuzzed out and condensed so it can fit on a screen. The system we're testing is in the middle, and all those tendrils reaching out are all those interfaces. Those interfaces eventually reach out and go to, a REST service or a SOAP service or a message queue or an application or a third-party vendor service or even our satellite communication system. So what I want to convey, this is not a trivial, hey, here's a single client with a service we're calling. This is a complex orchestration of many services and many events. But I'm going to give you the candy-coated view to kind of talk through our capabilities of how we kind of step through solving these problems. I call these the pillars. I'm going to rattle them off here real quick, and then we're going to step through them as environment isolation, test data management, service virtualization, and event orchestration. So our first one is environment. We took and partitioned off our own environment called CERT, short for certification, and put all of our applications in that environment. Next, we used a test data management tool, just TDM, to solve all our database problems. How we solve those problems, we're actually taking and some core features we're actually subsetting. So those initial databases might have 3 to 6 and 9 months or a years of data, depending on the retention policies for those particular applications. We just need 1 day. So our first step is subset to the 1 day we wanted to target. The other piece we use in here is obfuscation, PII data. So it actually strips and randomizes. So there's no PII data in our synthetic environment. The other cool piece of this that's very specific to us as an airline is date aging. So by combining those 2 key features of subsetting and date aging, every day our airline literally takes about 5 minutes to completely rebuild this environment, to clean it up, age it forward, and reload it across multiple databases. And one thing to add, these are multiple different database protocols. This is like Oracle, we've got SQL, and a couple others. So the tool is quite capable. The tool we used here was actually an IBM Optum, but we also use some of our own internal scripts as well to solve some of these problems. The next piece was the service virtualization. We talked about the passenger service already, but it was also aircraft. So the aircraft and the captain are always sending messages back and forth to the ground station. A couple of the scenarios we have here is that it was very specific. We're not just solving IT technical problems, but these are also business process problems. So our pilots have to work they get sent a flight plan from the system, and they analyze and they look at it, and they run the numbers for fuel and weight and balance, again, manually. That's essentially the double check. And so they have to respond to that. That's just not just an easy like request response problem. It's actually like 3 or 4 stages long, like initializing the aircraft, getting the flight plan, submitting the load plan, and then him acknowledging it. But then there's other synchronizing bits that are happening. So there's about 4 or 5 steps of back and forth that occur. Another piece that it does is once they've done that, he knows the amount of fuel it's going to take. And so it actually takes an auto response with converting fuel slips to fuel on board messages. So this is just all about breaking down all the little life cycles and analyzing those events and or request response problems. Okay, our last piece here is flight event automation. This is essentially the living, breathing heartbeat of the airline. It's not just those business processes done by flight attendants and pilots and gate agents, but it's also the flights themselves. In the industry, we refer to these as UI, which is out, off, on, and in. Essentially, the aircraft leaving the gate, taking off tarmac, then finally landing on its destination and pulling into the gate. So what we've done is this is an event modeled framework that does stuff in real time. All of these processes are time-based. And this fires those and keeps it all in that kind of like referential integrity across events, across time. Okay, so we now have this cert environment. This is all nice and clean. Things are flowing. Well, you think, but this is a best practice I'm going to throw out there is when we did this was initially based off of a recording. That recording might have had some irregular operations contained in it, or maybe some of the scenarios we needed weren't there. So we actually had to spend a few weeks after we started this. First snapshot was to actually massage that data in place, i.e. we had to throw in some more freighters. We only had one. We need to be able to test more than just one freighter. Also is to clean up the irregular operation scenarios that might have created some weirdness, because we don't want that every day. That's not normally how you run an airline, but we get to that here in a few minutes in our next area. So this is now all nice, pristine, and clean and running. This is now that magical step of the evolution. We now take those proxy recorders and put those on all those interfaces. We can now record a nice, clean data recording of our airline running. This is the magical step. We can now disconnect from all of that other infrastructure, all of those databases, web services, and servers, and there's so much infrastructure that takes place. You can now disconnect from it. So consider this IT cost avoidance. We can now just take this small data set and run this to another flight operations system in those other environments I was talking about. We started off doing cloning, as I mentioned earlier, but as those teams said they had different data needs, we just started using that recorded data and massaging into the state they needed to satisfy their needs. Okay. This is the real system that I'm talking about. This is our flight operations system. Down the left-hand side, you'll see aircraft numbers, tail numbers, and there's a little number up inside of there called D40, D30, D35, or 55, and that's essentially the D minus to the next flight. Across the top is time and UTC, and all the blue bricks are essentially, we call them pucks, but those are essentially our Gantt view of looking at our airline. Well, imagine if you were a tester and you wanted to test this flight out here. This presents several challenges. First of which is you got to wait until later in the day to test that particular market. Well, what if you find a defect? Okay, this compounds the problem. You have to wait for the developer to retest. Then you have to wait to retest. And what if somebody else has a test case against this? You can see that this now, even though with this nice clean recording, you now have a different problem. Even though it's consistent, you still have a constraint of not enough test data. Well, told you about our little evolution of using that recorded data. We were able to get feedback from the training team, and given the scenarios they want, we were able to load up using those base sets of messages and then applying our engineered data transforms to them, provide an airline that can now go in parallel. So if you look across the left-hand side now, all those tail numbers are sequential. They're all in the same D- state. All the flights follow a predictive pattern. And what this gave us is massive testing and training capabilities. What you see here is a lot of flights. When we first loaded this up, we think we came up with about 4,800 flights in all. Well, to give you perspective, Delta, one of the biggest airlines, has 6,000 to 7,000 flights a day in production. We were essentially 3/4 the size of production in just our little test training environment. So that created some performance problems because we're not at that scale. So we had to thresh or reduce the data a little bit. And so that's why you see this checkerboard pattern here. And so what this is just when you have control of the data like this and it's so engineered and so predictable, it's a lot easier to work with. We essentially could half the amount of data in the environment just by doing what we call a double div mod distribution, but it's really just saying, let's take the even number aircraft and disable the even number flights, and take the odd number aircraft and disable their odd number flights, which now reduces, halves the amount of data in the environment, but it's still available enough for everybody to keep working. Alaska Airlines prides itself on being essentially a real-time logistics company and running an on-time operation. The people on our front line have been trained in this. When I checked a year later, they said that 3,000 people had been trained using this environment. Checked back a few years later, it was 5,000. I don't know where it's at today, but it's probably in the 7,000 to 8,000 framework. And that allows us to essentially use these approaches, not just to solve testing QA problems, but also to solve operational training problems. Okay, so that's our old world. That's what we were kind of doing from 2014 to 2017 window. But in 2017, we started adopting, taking these approaches and really dialing on the data to do what we call engineered data. Again, it's using a lightweight web service with this prescribed data as its backend. We have some really cool capabilities around complete teardown that actually build up the files, run them through the system, and populate the databases in about 1 to 2 minutes. It's even faster than those other solutions we've built. What's great about that is we actually put that control of that data in our customers' hands, so they don't need to ask me to do anything. All they have to do is give me the scenario once, then I put it in their hands, and they can toggle it and say, I want the environment to be like this. I want to do long-haul flights. I want to do short-haul flights. I want to do freighter flights. I want to do milk runs. They now have all these capabilities at their fingertips to rotate the data in the environment. We still leverage a lot of SQL stored procedures because we're very SQL strong in essentially analyzing and structuring our data. Therefore, we use SQL agents, but our newest evolutions are actually using Azure functions to do that work for us. This last bullet point, I just want to talk about if people are on the call that understand what that is. This could be its own presentation. It's highly capable. It's essentially doing pipelining engineered data. Part of our flow was to create the SQL database of this engineered data that I'm going to show you next. That SQL data can now be built as a DAC pack in Visual Studio, but think also your ADO pipelines, which will then get pumped to a Docker image and then pushed to a container registry, which at that point, any developer could now pull down these engineered data solutions and then do testing and development against purely synthetic data at scale on their local machines. Okay, so our solution showcase. This is all the new stuff we've done around engineered data, our new framework. Ops 360 is our new, it's not the flight op, it's a smaller piece of our flight operations management tooling. The two key pieces here is data generator and message replay. Data generator is an Azure function. As I mentioned, we're now adopting more of these cloud capabilities. It runs every day. It does three things. It generates flights, generates events, which is considered like our sunny day base event model. And its third step is based on the configuration, we'll now do complex transforms to create exception scenarios. And I'll get all these things here we're going to go into in detail here in a few minutes. Next is our message replay. Also, it is an Azure function. It runs every minute and essentially reads from the database of all those messages that the data generator built and places them on their specific queues at the time they're needed. And it updates the roses process, so when it reads the next time, it's only picking up net new data. So let's look at generate flights. The generate flights component itself is actually a stored procedure with some complex algorithm logic to it. It does get invoked by data generator, but the key part of it actually reads that config from our flights config table. And can think about flights config as a way for us to essentially parameterize the definition of an airline. Once it runs the algorithm and outputs those flights to our flights table. So this is, sorry about the nomenclature here. This was originally designed as a stored procedure that passed parameters, but it's now in a table. So we're now building blocks of how do you define an airline? Well, first we've got our, when do we want it to start? And how long is that flight going to be? And what's the kind of distance or padding until the next flight? So that now gives us one building block. This is one piece of data to essentially say, I could now create an airline of one flight. But we wanted to get bigger. So how do we do that? Well, those early approaches we told you about were doing sequential data across time. So we now have that same tail number. We'll sequentially, using those data parameters, start stacking on more flights after it. But now we want to solve parallel problems. We want to have more than just one sequence. So we can now have another parameter for number of aircraft. Okay, so now we can build bigger blocks. Okay, this is, just so you know, all of this engineering design was actually around performance testing some of our systems. And this is that approach. And so anybody from the performance background will really understand this, because this is usually how you set up your ramp ups of however many concurrent clients you want and spinning up at what interval. Well, that's typical from a client perspective. We're actually now approaching this from our data creation perspective. So we can now create a virtual airline at scale. Anecdotally, if you look at this, this would now start creating a slanted view. And go into this here for a second. So if you were to keep applying that algorithm moving forward, you would get this kind of, those four stages, then they would end, and then the next bank of flights would go, and then this is a way of looking at it. But this isn't the way I want you to look at it. Think about this from the performance perspective. As those are going, you're actually now essentially defining a peak. And so this is why all of this data comes into play. We've essentially parameterized all these capabilities for defining what the airline looks like, and we can achieve a very peak number for how many departures we want to have at a time for testing to pair up with our other performance testing. So instead of us trying to performance test what the airline looks like today, we can performance test what our airline looks like in 5 years. Building on this a little bit, this is more specific to the airline. This may not interest you as much, but this is specific to us. We need this kind of capabilities since this is all an algorithm. We have round robin aircraft, which essentially go from point A to point B, then back to point A, while maintaining the same flight number. The next one is multi-leg. That's more like a unidirectional while maintaining the same flight number. So we've got our AS-15 goes through its first 3 stages, and then our algorithm likes to keep all the data linked. So it actually increments the flight number for that last stage to bring it back to home base. And then also a circle flight, which maintains the same flight number during the entire looped rotation. And of course, I skipped over above. It's pretty straightforward, but the blue box is same aircraft having a sequential flight number for each stage. Again, this is specific to the airline, and one of the cool things I wanted to bring out as a call out, we are pushing our capabilities to the edge. We started off working really close to the system, and as our capabilities mature, we actually are now adopting, by doing this with the native formats the industry uses. In this instance, this is actually a SIM file, which is a standard scheduled information module. And it's how those airlines, as I mentioned as being partners, can exchange their schedule so that they can book those connecting flights. It uses this concept of onward flight number for the next day. And so our algorithm automatically, since it is a pretty basic algorithm, but it allows us to still test it and be functional, works this way. And it's given us really cool capabilities by actually building industry standard engineered data files that we can load into our systems. Okay, so that was the generate flights component. Now we're taking the next step to step 2, which is generate event space. This is that life cycle of events, the out, off, on, in that I previously mentioned. The one at the top is SFA, which is short for schedule flight add. And it would have generated all these flights and all of these data bits specifying what those flights. So this is actually the framework. And we now have our times for when the actual out message value would get recorded, and it kind of gets inherited in all messages past that point. So as time goes on, it keeps carrying in all those previous events that occurred. And on the far right, I would say type. These are inserts because this is the base event. There was nothing before it. It's just doing an insert. Okay, so we now have our base events. Well, let's now start creating a more complex scenario. This is now how we start doing those exception scenarios. So our framework now allows us to simulate these exception scenarios. And what we're going to do today is a div, which is short for divert. So instead of going Seattle to LAX, we're going to go to Seattle to San Diego. You'll notice on the far right, this is a insert event, but also a transform. So it actually puts a new message into that replay table that's of a div type, but then it actually goes and grabs all the downline messages that occur after that and applies the transform that you see in red and changes the destination of those to San Diego, but also changes the ops types to divert. Okay, when you're asking yourself, okay, Ryan, you now have diverted this flight, but this is going to a different station. That's not realistic that it could make it to the other station the same amount of time. Like, you're right. Well, we can solve that. UD is short for unknown delay. This is an event that we have in there, and I call it a stealth event because it doesn't actually, there's no such event as called unknown delay. All we're doing is doing a transform of downline events. So this one is a unknown delay based on the on event, and we want to add 30 minutes to it. And so now that on message and all those downline messages has now been updated. You're like, well, Ryan, this still doesn't make sense because it's now landing at 1300, but it's inning at 1240. So it's totally off. Well, all we have to do is keep on bolting on our customized events to this to fix that. So we now apply an unknown delay on the in message and push it back 30 minutes as well. And so what this framework essentially does is it builds up all of those base inserts, and depending on the scenario that you describe, will apply the transforms to all the downline messages to simulate what you need. And this is a what I call our design considerations document. That is essentially a place I use to gather all of those different rules for those events. Not to scare you, but there's about 30 more columns to the right and about 20 more events below this. But you can kind of do a quick glance of this and see all the custom business rules we have in our framework to accommodate everything that we're doing. One key one we call out is the conditional actual times. That actually, as you start inserting new events, it actually detects its context in relation to other events that have already fired and conditionally displays those values. Payload transforms. This is where a lot of the work is happening and for building this framework. So there's a lot of, as soon as you start doing these unique scenarios, you now need to accommodate for that. And there's a lot of places in those downline messages to start adding new objects, removing objects, or applying date time transforms to them. Using this framework, we were now able to simulate any scenario that the business has come up with. We did not have these capabilities before, and I just can't say it enough. Like, this is a lot of hard work. Me working with the Ops 360 team, they were all the developers building the actual functions, but which was great because as a developer perspective, we got to bring them into actually doing data. So when they develop a function, they're more on the consuming side. Hey, I get a message, I need to make it and push it to a database and apply some business logic. But we now brought them to say, step to the left. You now need to be able to build data that could exercise your function. So now that they knew what they were consuming, they now have also to build something that produced what they were consuming. So this is a really good exercise for us as a company for working with our developers to give them new capabilities, but also for our product owner team. By them giving us all their scenarios, we were able to now build all these custom events to handle anything they need. What's next? Well, we've been doing this engineered approach for several years, since 2017, and these new capabilities we want to take this across to our entire test environment. But that's a big task, a big ask as well. And so in practicality, we're going to probably incrementally implement it across different applications so that they can abide by the particular data model. Best practices. I covered on some of these as we're going along, but I'll go into some more here, is create an isolated environment where you can go do this at, so you're not fighting with organic, real data coming in. You can still analyze that data elsewhere, but just you don't want to do it here. Have we? Well, we have done data blending. It's not fun, but it is doable. It requires a lot of extra work on your engineering folks, because you'll see, like in our example, we'll see some flights that come in all looking nice, precise. Then it'll go to organic data, looks all kind of messy, and then back, and it's kind of hard to troubleshoot, like, where did this data come from? Next is analyze. My background is actually in systems engineering and protocol analysis, so that's what really helped me in this role. But just reviewing architecture documents, really understanding these complex applications and what they connect to and where that data comes from. Also reviewing the code. We've spent many an hour of doing code review to figure out what were they trying to do with this, and kind of tells you where what it's trying to do and where it's going. Configurations are the same. When we were trying to troubleshoot some environments to get them hooked up, sometimes they would get pointed to a developer machine or another test machine or QA or some other location to pull in a config or feature. And so we had to really hammer that out. And we actually had a release coordinator help us with that. Analyze the data. And this is the place where I spent the absolute most amount of time, is to understand your environment. What you're usually testing, you're actually usually testing the data in your system. But for us, since we're an airline, real-time logistics, business processes, we had to analyze events as well, and a little bit of Fiddler and Wireshark analysis of traffic. So we couldn't understand how a few things happen. Like, why is this one thing firing? There was like a callback process elsewhere that was making data kick off. So we had to use not just, business knowledge and architecture knowledge, but also just some good old analysis. Resolve your data issues. I covered this a lot up front. Resolving your event issues. Again, it depends on your market. What does that eventing look like? Are you doing, pure orchestrated events or just business processes? And if you can, use engineered data. I didn't really dive into that too much in this presentation, but it's really getting to using patterns and numbers and creating derived relationships in data to solve these complex problems. You can do build up, tear down. That's better for you because that's super fast and tight. Leverage your SMEs. We got so much. I've been in this space for a long time, but even on this most recent project, working with the SME, I got to have a nice section of understanding their perspective of how the event should be consumed and interpreted. Even though my framework handled it, it didn't really matter to me, but it allowed me to understand how he thought. The last piece is thinking big. For us, these are all big solutions. If we were to try to solve this by looking at one service and then going to the next, we would lose visibility and have to do a lot of rework to maintain it under the same umbrella. And that's kind of like why the same problems everybody runs into in the real world, by this system's not in sync with this one and it behaves different. By having this think big approach to solving these problems, you can now kind of keep it all under one umbrella. And
Ryan, thank you. Thank you
stay
so much.
available on your team and how you run it, if it's purely agile or if you're trying to solve these bigger problems.